In this session, we are going to see the introduction to quantum computing and its future applicability. So here are the aspects which the quantum computer is related: the algorithms, security and reliability. So we all know the quantum computing is the upcoming future trend of the computers. So where it can process in a multiple way and in a span of microseconds provides the tasks and resolves the issues in a dramatic way which can even we cannot imagine the speed of the computing. So what is the algorithms that we are going to use in the quantum computing? So algorithm is basically a step-by-step process. It is the set of instructions or rules that going to give a solution to a problem or a task is to be resolved. These are the instructions we give in a step-by-step process, and actually it is like a recipe. The input data is converted to the output data as per our desire. So the security aspect, what is the security aspect? And we all know the data whatever we process need to be secured. It must be secured. So the security aspect in this quantum computing, now in the current trend as per the modern encryption methods, the quantum computing as of now is not so secure, because see the cyber security standards like RSA and ECC are easily vulnerable or that can be broken in the future because of the powerful quantum computers and their high processing capacity. So there is an urgent requirement to go into the post-quantum cryptographic methods where we use cryptographic algorithms. So what is cryptography? Here the cryptography is nothing but converting the readable data into unreadable formats to secure the data. What are the unreadable formats? That is like lattice based and hash based systems. Simply here in cryptography, it is a science which converts plain text into ciphertext. So the cryptographic algorithms which we do this kind of conversion by using some mathematical algorithms. So the security standards can be improved only if you are going to develop the post-quantum cryptographic methods. So the next one is reliability. So the reliability is the utmost priority in computing. Whatever the data you process and the outcome must be reliable and authentic. So as per the quantum computing, we use qubits here, which we are in processing wise they have unlimited speed, but the outcome is also impeccable. Either it must give 0 or 1, yes or no. That is the outcome, but in the processing it uses both 0 and 1 simultaneously. So this is the introduction. We move to the next slide. So here are the table of contents which we are going to discuss in the next few minutes. So introduction to quantum computing, which we have seen already in the first slide. Quantum machine learning applications, and quantum machine learning is all about quantum computing mixed with artificial intelligence. So these applications are mostly in finance, healthcare and logistics sectors. In finance we may see the large computing of the data, especially profit and loss and balance sheets. So these are the applications. And in healthcare is the future prospect with quantum computing and as per the quantum scientists. So the processing, the synthesis of the new drugs, the molecular combinations, and especially with quantum machine learning is done in healthcare, and the bright future of healthcare is all dependent on quantum computing. So this quantum security, QKD versus post-quantum crypto, quantum key distribution. This is a communication technique which is hardware based and mostly uses quantum mechanics principles and properties of photons especially. So, quantum error correction. This quantum error correction is a vital set of techniques to protect quantum information from decoherence and noise. So, fault tolerant quantum computing, quantum machine learning algorithms, quantum cryptography, QKD fundamentals, quantum key distribution fundamentals, quantum crypto and its adoption and standards, surface code overview, conclusion and future outlook of quantum computing. We will see in the next few minutes what these are. Introduction to quantum computing. Qubits. Qubits are the units of quantum computing. Here they are represented by two states, 0 or 1, not individually but simultaneously. So 0 or 1 simultaneously which exist in a process, and the process is simultaneously executed in both yes or no ways. So qubits exist in a superposition of states. So what is superposition? See, this qubit behaves like a wave. So whenever two waves are superimposed, there will be a coherence of waves and thereby causing the interference. So interference is nothing but the superposition of two waves. So here they leverage entanglement also. What is entanglement? So this is the connection of two particles irrespective of their distances. So entanglement actually resembles the same quantum states of two particles. Quantum states are energy, spin and momentum. So when you measure the quantum states simultaneously of two particles wherever they are in the universe, so the quantum states are exactly identical, and this is the connection between the two particles. So whenever the quantum states of one particle is measured, it is automatically affects the second particle. So in this way the orthonormal basis states, see this qubit, the quantum state of a qubit is represented by two orthonormal basis states, that is we represent here, see the qubit is represented by so 0, and this is a bracket, and 1, two states, so individually. When the qubit itself is represented in a superposition way, that means combination of these two, so then we can represent the qubit as a wave function like this. So where alpha, beta are probability amplitudes and also they are complex numbers. So next, quantum speed up. To speed up the processor, that means the calculation time. See, the interference patterns are used to amplify the correct answers. Interference patterns. So here always the interference occurs whenever two coherent waves are superimposed. They form crusts and troughs. If you consider the crust as a correct value, that means desired value, that is represented by 1, and the trough is always represented by 0, that is answer is no. For a question, if you say what is the probability, yes or no, yes is represented by crust. When you take a wave like this, it is represented by the crust and this is the trough. So the wave function, a qubit is like a wave function, and see the key primitives include phase estimation. Whenever the wave propagation occurs and the speed of the quantum process actually depends on the crust and trough. So phase estimation and amplitude amplification. Whenever the two waves superimposed with coherence and same phase and same frequency, the amplitudes are multiplied, so they actually get up added. So this amplification is nothing but increasing the amplitude in a crust. So this is the quantum speed up process, uses the interference patterns to amplify the correct answers. Hardware reality. What is the hardware that actually resembles the quantum computing? See, currently that noisy intermediate scale quantum devices, NISQ, are noisy and error prone. Why they are noisy means these devices actually have a capability of 52,000 qubits. They are not so advanced. They are prone to fault tolerance. That means there will be errors. So the noise is because of the errors and quantum decoherence. So we need to actually go for quantum error correction. So these are not capable of 100% quantum error correction. So we'll move to the next slide. See, QML core algorithm families. See, these are the core algorithms used in quantum computing. The first one is VQE, Variational Quantum Eigensolver. This algorithm depends purely on the energy concept. The quantum mechanics is calculation of quantum states, that means energy, spin and momentum. Here the energy takes part in this algorithm, and this hybrid quantum classical algorithms. So this is a hybrid algorithm which uses both quantum and classical computing. So designed to find the ground state energy of a Hamiltonian. See, Hamiltonian is an operator of a system which gives the energy of a particular system of particles. So it includes both kinetic energy and potential energy. So this Hamiltonian is an operator. It minimizes a cost function. So minimizes a cost function. That means it is not actually related to cost or price. This is a method which gives the difference between the actual value and the algorithm measured value. So this minimizing by this cost function means we are minimizing the error between the actual value and algorithm calculated value by adjusting parameters on a quantum circuit. It itself adjusts the energy parameters by calculating the Hamiltonian. So this method is useful at the ground level of any system. Here next one, quantum approximate optimization algorithm. So optimization is considering the solution and its optimal value, not exact value. So combinatorial, it is a set of combination of solutions. So by the combination of solutions, a set of solutions, we need to pick the optimum one. So here, by alternating between cost and mixed Hamiltonians, how does this QAOA algorithm works? Means it actually adjusts itself between the cost function and mixed Hamiltonian. There is a lot of set of Hamiltonians, that means operators for different systems, and they produce a lot of solutions, a combination of solutions. So we need to find out an optimal solution from that set of solutions. So this algorithm uses problems by alternating between cost and mixed Hamiltonians. Last one, quantum neural networks. So parameterized quantum circuits, these are actually related to classical neural networks trained similarly to classical neural nets. Techniques include data re-uploading. See, this re-uploading is done with the help of quantum kernel algorithms. The quantum kernels is a method to identify the similarities between two data points or any two other different points, so how much they are similar to each other, to process data in high dimensional Hilbert space. So high dimensional Hilbert space is this is a vector space, multi-dimensional, infinite dimensional. Hilbert space allows inner product. That means calculation of length, breadth, angles, everything. So in this kind of a multi-dimensional space, this quantum kernel method, quantum kernel algorithm is used as a part of the neural network to find out the solutions of that multi-dimensional space. So okay, we will move to the next slide. Here we see QML applications by industry, quantum machine learning. So quantum machine learning, as we discussed, is a combination of quantum computing with artificial intelligence. So here are some applications. You can see this field where there are applications including pharma, finance, auto, energy, chemicals and logistics. Here how it is used in finance and fintech. Portfolio optimization. See, portfolio in trading is nothing but a collection of stocks, currencies, bonds, commodities, derivatives. So these kind of collection of all the finance items is called a portfolio, and high frequency trading leverage quantum algorithm like QAOA, quantum optimization algorithm, to find global minima. See, what actually it is in trading, high frequency trading, where the stocks are traded in more times in a particular time. So there is a high risk. See, the high risk landscapes or the fields and complex risk. The complexity, see, the invariable, the variables are more, the risk is more. So in trading, the risk is more. To set it into minima, at minima level, there were previously Monte Carlo simulations were there where classical computing is used. Though based on Monte Carlo simulations, the prediction of outcomes, the probability of different outcomes was done at a particular pace, considering so many complex fields. So here the QAOA algorithm finds a global minimum. Minimum means minimizing the complex risk in trading. This is one of the important application in AI related quantum computing, where nowadays you are getting so many reels in social media where you can actually trade without knowledge with the help of artificial intelligence. So how it is working. Next, healthcare and pharma. Accelerating drug discovery via VQE, variational quantum eigensolver VQE, by accurately simulating molecular structures and protein folding, identifying molecular similarity for repurposing existing drugs efficiently. So what it is all about is drug discovery. It is not an invention, it is a discovery. We have already some existing drug formulations. So these drug formulations are revisited, re-identified. So molecular similarities. The similarities are identified with the energy parameters. That is what VQE is all about. It uses, we already discussed, it uses the cost function and Hamiltonian parameters, where the energy parameters meet the molecular structures and identify different combinations in the existing drug itself. So here the existing drugs manages it efficiently to further ailments in the medical industry. So the last one, AI optimization. So artificial intelligence can be used optimally. Okay, optimally used. That means we can get the solutions when there are lot of probabilities are there. We can optimize the solution with the introduction of artificial intelligence. Quantum feature maps. See, enhancing classical AI with quantum feature maps. These are kernels. We already discussed. Kernels are a method, see, to identify the similarities between different points or 2 points or more than 2 points to process high dimensional data. If in a particular data where there are so many dimensions like logistics, like pharma, like HR, so all the dimensions might be having some data points where there are some similarities. These kernel algorithm will find those similarities. Applications include generative models for synthetic data and complex logistics routing. Okay. So complex logistic routing. What is complex logistic routing? Here in logistics, you need to have so many solutions for the proper delivery of the goods. So here the applications include generative models for synthetic data, synthesized data. Now the data which is given to you as it is from a particular firm or organization is the data which is not organized in any proper way. So synthetic data is also we can analyze and come into a particular solution using artificial intelligence. So here is the outcome of these applications used in the industry. Thank you.